Hi, I'm Roger Fawcett, CEO of Omnitech, and today I'm going to introduce our Dpu IP. So first of all, to say a bit about Omnitech. So Omnitech is a leader in FPGA IP. We do design services for video, vision and AI, and we have highly skilled staff with a particular expertise in DSP design. We also do video test and measurement, and we have about 50 staff that have been growing rapidly and have achieved 3 Queen's Awards along the way. To give a further background to what we do, you can see here our Flex board, and on this board we are running a GPU-like application for video warping. And what we've been able to achieve is an extremely small footprint design, in this case in a Zinc 7010 device, which is the lowest end Zinc FPGA device that exists, and which has enabled us to penetrate into ASIC markets using highly optimized FPGA design and also competing with GPU technology. And the DPU builds on this heritage of highly efficient DSP video design to address the AI market. So today we're making 2 announcements. The first one is the DPU, and I'll talk through the architecture of that very shortly. The second announcement is that we are sponsoring a DPhil research scholarship at Oxford University, which will be particularly focusing on research into FPGA applications for AI algorithms. So the Omnitech DPU is a highly optimized FPGA IP core, which is programmable via software overlay framework. So it can be programmed using standard Python and TensorFlow, familiar to a software programmer, but takes advantage of the highly optimized Omnitech IP. So this first release is addressing convolutional neural networks, but further releases will address different neural network topologies. And being an IP design services business, we're able to augment this AI IP with further video and vision processing to produce complete system level designs. Here you can see the overall system diagram of the DPU. So on the right you can see that we can configure the IP and create highly optimized IP, and this is created by Omnitech, and we can configure for different workloads and so on, and also add our own video processing and vision IP to create complete system solutions. On the left you can see that the end user can program this via standard Python and C++ programming under TensorFlow and with other frameworks to follow, meaning that they can write code, compile it with our compiler, quantize weights, and this flow runs in a matter of seconds, so there's no FPGA redesign work required by the end user, and then the resulting microcode will run on the DPU system, giving optimum performance. The very efficient IP can of course be used to create a large design for data center or large server applications for the ultimate performance, but equally the efficient design can be used in a very small IP core with lower performance and a low power embedded design, getting the maximum performance per watt. And this enables more space available in FPGA for example, system integration of other IP. The initial release of the DPU is built around the VU9P Xilinx FPGA, and to talk through some of the key points about that and the general advantages of FPGAs. Firstly, you can see here that the VU9P actually contains over 13,000 int8 multiply accumulate units in the DSPs, which can be clocked at up to 891 MHz. It also contains significant on-chip SRAM and a massive programmable logic array that can be configured optimally for different neural network workloads. The complete programmability of FPGAs has many advantages for neural network applications. So first of all, there's a good deal of research in arbitrary precision neural networks showing that they can run not just at int8 but at lower precision as well. And an FPGA is the only architecture that can be adapted to arbitrary precision without any loss of efficiency. FPGAs have also proven to be very effective in creating large DSP processing arrays which can run very low latency neural network architectures. Also very importantly, different neural network topologies such as CNNs and MLPs and RNNs require different types of processing, and again the FPGA architecture is the only architecture that can adapt and completely rewire to address these different types of topologies. And in addition to that, other IP can be added. So for example, an ASIC designed to do neural network processing can only do that generally. It can't do anything else. Whereas if we wanted to add our warp processing or video processing or connectivity, that can also be added within an FPGA design. The overlay programming interface that we've implemented enables a software programmer to write regular C and C++ and Python code within a TensorFlow framework and program the device without any FPGA knowledge. And finally, as we've talked about, because an FPGA can be completely rewired for different applications, it means that we can address as yet unknown future requirements of AI and neural network applications. So for example, here you can see in a schematic illustration 3 different types of neural networks. We've got RNNs here, which are typically used for temporal processing, speech type processing, MLPs, which are used for correlating relatively arbitrary inputs, and CNNs, which are generally used for image processing or processing of 2D arrays. And as you can see from these illustrations, they have different wiring of neural networks. And we can take advantage of that in the FPGA and apply different processing techniques to produce optimum performance of these. And just to give 1 or 2 examples of that, CNNs have shared weights and great array parallelism, which is one thing we can take advantage of. Whereas typically RNNs and MLPs often have a lot of redundancy, and therefore you can take advantage of weight, sparsity and pruning to improve performance. And more importantly than that, as we said, in the future we don't know what direction neural networks and AI will go, and from what we've seen so far, FPGAs provide the most suitable technology to address the as yet unknown requirements. So during recent years, we've seen very significant changes in neural network architectures with significant improvement in accuracy and so on. And this has created different processing requirements. For example, only 4 or 5 years ago, everybody was processing in floating point 32, whereas now people are using low precision designs. And this creates a great challenge when designing a chip. So many chips have been designed for certain precision only to be outdated by newer research. An FPGA, because it's purely programmable, can be adapted very rapidly, which means we can address these new requirements very quickly. Whereas an ASIC may take several years to implement a design and get it to market, we can take advantage of any new algorithms and optimization techniques and have them to market within a matter of months. We can illustrate this point by looking at this extract from the first Google TPU paper. So as you can see here, the peak performance of the TPU is 92 teraops. But for example, if you look at CNN1, it achieves only 14.1 teraops, which is around 15% efficiency. And in fact, if you look at the other topologies such as LSTMs and MLPs, you can see the performance is significantly lower, only achieving around 10 or 15% efficiency at best, some of them even lower than that. Whereas in an FPGA architecture, we can completely rewire the logic to produce optimum designs for all these topologies. As a further illustration, this first version of the TPU was designed around in-tape processing, but since then there's been significant research in varying different bit precisions and floating point, block floating point, that this design is not able to take advantage of with any efficiency or possibly even at all. Omnitech has a great heritage in FPGA design and DSP processing algorithms, but in this fast-moving world of AI research, it's very important for us to keep on top of the latest research and actually develop new algorithms and do new research ourselves. And to this end, we've launched the Omnitech Oxford University Research Scholarship to perform collaborative research with Oxford University specifically into this area of using FPGAs for AI applications. To wrap up, the DPU provides the highest performing CNN inference performance on an FPGA. It provides performance, cost and power advantages for all designs. It's delivered on a platform which supports optimization of the network for the workload. It is future-proof because it can be rewired for different topologies. It provides rapid time to market and facilitates system-level integration, including addition of video and vision IP. Thank you very much.